In the earlier lectures we have seen formulation for 3 node linear triangular element, and in the next 2 lectures we will be looking at formulation for higher order triangular elements. A relatively simple method is available for deriving shape functions for higher order triangular elements, and that method requires what is called special coordinate system, natural coordinate or area coordinate system. So, we need to learn that before we proceed with formulation for higher order triangular shape, formulation for higher order triangular elements for deriving shape functions and subsequently for deriving the element equations. So, in the next 2 lectures we will be seeing what are these natural coordinates or area coordinates and formula for deriving shape functions for triangular elements. This formula you can even use for 3 node linear triangular element, and also it can be used for deriving shape functions for higher order triangular elements. And then as usual, similar to what we did for quadrilateral element, we look at isoparametric mapping concept for triangular elements, and then numerical integration to derive area integrals or to obtain area integrals and boundary integrals when we adopt triangular elements for discretization, and also at the end we look at quadratic triangular element with curved boundaries. So, now let us start with understanding this natural or area coordinates for triangles. So, this is what I mentioned. Consider a triangular element with corners labeled as 1, 2, 3 as shown in figure. X, y coordinate system is shown and the 3 nodes are numbered as 1, 2, 3, and the coordinates of node 1 in x y coordinate system are x 1 y 1. Similarly, coordinates of node 2 are x 2 y 2, and for node 3 they are x 3 and y 3. Instead of expressing coordinates or positions of these nodes 1, 2, 3 in terms of x y coordinates, we can also express in terms of what are called natural or area coordinates. To understand that, let us consider a point P inside the triangular element like the way it is shown in the figure, and if this point P is connected with each of these vertices 1, 2, 3, and based on area opposite to node 1, area opposite to node 2 and area opposite to node 3, we define what are called natural or area coordinates. And if you take any point, this point need not be inside the triangle, it can even be on the boundary of the triangle, boundaries of the triangle. So, you can easily verify that this that is area opposite each of these nodes is going to be unique for any point inside or on the boundary of the triangle. So, based on that we define what are called area coordinates. Coordinates of any point P located at x y can be expressed in terms of area based on coordinate system denoted by L1, L2, L3 defined as follows with reference to the figures below. So, the triangle which is shown earlier is reproduced here, except that point P is connected with each of the vertices by a line, and area opposite to node 1 is denoted with 1. So, now let us see how L1 is defined. I hope you understood what is area opposite to node 1, which is clearly denoted with 1 in the figure, and similarly area opposite to node 2 is denoted with 2, and area opposite to node 3 is denoted with 3. So, now let us see how L1, L2, L3 are defined. L1 is nothing but ratio of area opposite to node 1 divided by, or ratio of area opposite to node 1 to total area, or area opposite to node 1 divided by total area. L1 is area of shaded triangle. Here it is not shaded, but it is denoted with 1, that is area opposite to node 1 divided by total area denoted with AT. So, area opposite to node 1 is denoted with A1 and total area is denoted with AT. L1 is defined as A1 divided by AT. So, if you consider any point, this L1 is going to be unique, because once the point location changes, point P location changes, area opposite to node 1 automatically changes. It is not going to be unique, sorry, it is going to be unique for every point, and it is not going to be same for any 2 points. And similarly, L2 is defined as area opposite to node 2 divided by total area, and L3 is defined as area opposite to node 3 divided by total area. So, this is what a coordinate system based on area, and instead of describing location of a point with respect to xy coordinate system, we can as well express the location of point in terms of L1, L2, L3, because L1, L2, L3 values are going to be unique for any point. And now it can be easily verified if you sum up L1, L2, L3, it is going to be A1 plus A2 plus A3 divided by total area, whereas A1 plus A2 plus A3 is equal to total area. So, L1 plus L2 plus L3 is going to be 1. And also it can be easily verified that if point P coincides with node 1, that means we are trying to write L1, L2, L3 for node 1. In that case, area opposite to node 1 is going to be total area. You can easily see that by imagining point P coinciding with node 1. In that case, area opposite to node 1 is going to be total area. In that case, L1 is going to be 1 and L2, L3 are going to be 0. Similarly, if point P coincides with node 2, L1 is going to be 0, L2 is going to be 1, L3 is going to be 0. And also when point P coincides with node 3, L1 is going to be 0, L2 is going to be 0 and L3 is going to be 1. So, with this understanding, mathematically the triangular or triangle natural coordinate system are related to xy coordinate system as follows: x is equal to L1 x1 plus L2 x2 plus L3 x3. Whether this relation is correct or not, it can be easily verified by making x coincide with any of the nodes. Suppose this point coincides with xy coordinates coincides with coordinates corresponding to node 1. In that case, L1 is going to be 1, L2 is 0, L3 is 0, and this equation perfectly correct. So, similarly, y is equal to L1 y1 L2 y2 L3 y3. This can also be verified. So, we have three relations. One is L1 plus L2 plus L3 is equal to 1. The second relation is x is equal to L1 x1 plus L2 x2 plus L3 x3, and the third relation is L1 y1 plus L2 y2 plus L3 y3 is equal to 0. Sorry, y is equal to L1 y1 plus L2 y2 plus L3 y3, and we can write all these three equations in a matrix form. We get this: x y1 put in a vector is equal to matrix consisting of x1 y1 1, x2 y2 1, x3 y3 1, and L1 L2 L3 put in a vector. And we can, using this relation, we can back calculate what are this L1 L2 L3 for a particular point x y having coordinates x y by taking inverse relation like this. Since we know the coordinates of all the three nodes, node 1, 2, 3 are the vertices of the triangle, we can easily figure out what are these x1 y1, x2 y2, x3 y3. So, we can easily calculate or we can easily find what is this L1 L2 L3 in terms of x y for any point having coordinates x y. And here further this can be so solving previous equation for L1 L2 L3, L1 is given by this, where the symbol indicates determinant of matrix. So, L1 is determinant of matrix consisting of components x y1, x2 y2 1, x3 y3 1 divided by determinant of matrix consisting of x1 y1 1, x2 y2 1, x3 y3 1. And if you verify that these determinants are nothing but twice the area opposite to node 1. One of the determinant is twice area opposite to node 1 and the other determinant is twice total area of triangle. So, L1 is ratio of area opposite to node 1 divided by, or area opposite to node 1 to total area, ratio of area opposite to node 1 to total area, and that can be calculated using the determinant of these matrices, which we can obtain from the information about the nodal coordinates of the particular triangular element. So, this is how L1 can be calculated. Similarly, please note that this is obtained from the previous equation by inverting the equation or the solution of the previous equation. Based on that we got this L1. Similarly, we can find L2 and L3. It is easy to remember these formulas for L1, L2, L3. If you see the denominator, we have determinant of matrix having components x1, y1, 1, x2, y2, 1, x3, y3, 1. And if you are trying to calculate L1, you copy whatever is there in the denominator to the numerator, except replace the first column of the matrix with x, y, 1. Similarly, when you are calculating L2, replace the second column of the matrix in the numerator with x, y, 1. Similarly, when you are calculating L3, after copying whatever is there in the denominator to the numerator, replace whatever is there in the third column of the numerator, replace that with x, y, 1. So, that is how you can easily remember these formulas for L1, L2, L3. And also from the definition, it is easy to see that area coordinates remain constant along lines drawn parallel to sides of triangle. So, it is illustrated here. So, if you have a triangle and if you try to draw lines parallel to each of the sides, along those lines the area coordinates remain constant as indicated in the figure. This can be easily verified using the formulas for L1, L2, L3. So, this is how one can find area coordinates of any point. So, now the procedure for deriving shape functions for triangular elements is based on this concept of area coordinates or natural coordinates. So, shape function formula, that is that we are going to look in a while, requires each node be represented by three subscripts related to L1, L2, L3 values at each node. So, at each node we need to find L1, L2, L3, and we need to use those values of L1, L2, L3 for deriving shape functions using the formula that we are going to look now. So, now let us look at the procedure shape functions for triangular elements. As I mentioned, this procedure is applicable for both higher order triangular elements as well as the linear triangular element that we already looked at. So, this is how this procedure goes: node numbers based on natural coordinates. Following steps are used to develop three subscript numbering schemes for nodes. We look at some steps and then we look at make them clear by looking at some example and then come back to the formula. So, that is how we will proceed. So, first step is find L1, L2, L3 for each node given a triangular element. Normalize all coordinates by multiplying with a constant to convert them to whole numbers if necessary. So, this step of normalization is only required if necessary. So, normalize all coordinates by multiplying with a constant to convert them into whole numbers if necessary, and this point will become more clearer when we look at an example. Label each node of triangle as L1, L2, L3 using the normalized coordinates. So, to understand these first 3 steps, let us take 2 examples and try to understand these 3 steps before we proceed further with this procedure of deriving shape functions for triangular elements. So, now let us try to understand how to find L1, L2, L3 for each node, and also how to, or if necessary, how to normalize this L1, L2, L3, and also how to label each of the node as L1, L2, L3. A 3 node triangle with actual and 3 subscript node number is shown in figure below. So, the figure on the left hand side is numbered as 1, 2, 3. Imagine that to be an xy coordinate system, and the figure on the right hand side is numbered, the nodes are numbered using 3 subscript numbering scheme. So, how this 3 subscript numbering scheme is obtained, let us try to understand. So, the 3 subscripts are based on the following reasoning. This is the triangle that is given having nodes 1, 2, 3, and I already explained at node 1 L1 is equal to 1, L2 is equal to 0, L3 is equal to 0. So, that is how node 1 is numbered as 1, 0, 0 in 3 subscript numbering scheme. Similarly, at node 2 L1 is 0, L2 is 1, L3 is 0. So, node number under 3 subscript numbering scheme for node 2 is 0, 1, 0. Similarly, at node 3 L1, L2 value L1, L2, L3 values are these. So, node number for node 3 under 3 subscript numbering scheme is going to be 0, 0, 1. And here you can see for this particular 3 node element, all the area coordinates, that is L1, L2, L3 are whole numbers. So, there is no need to normalize. So, we can directly write L1, L2, L3 side by side to get this 3 node or 3 subscript numbering for each of the nodes of the given triangle. So, this is how we get this 3 subscript numbering scheme for this 3 node triangular element. So, now let us see higher order element 6 node triangle with actual and 3 subscript numbers, and the element is shown here. The intermediate nodes are placed at mid sides. That information is required because unless we know where these intermediate nodes are placed, it is difficult for us to find L1, L2, L3 for that particular node. So, that information is given. Intermediate nodes are placed at mid sides. So, the actual 6 node element is 6 node triangle element is shown, and also for that 6 node triangle 3 subscript numbering scheme is also shown on the right hand side, and this 3 subscripts are based on the following reasoning. At node 1 is similar to 3 node triangle, L1 is going to be 1, L2 is 0, L3 is 0. Now, at node 2 same thing as for 3 node triangle, and at node 3 same again as for 3 node triangle. Now comes the new thing, that is at node 4. Imagine node 4 joining or joined with each of the vertices. Already node 4 is along side 1 2. So, it is already connected with 1 and 2, and now connect by an imaginary line node 4 to node 3, and it can be easily checked that when you do that kind of joining of node 3 to node 4, that imaginary line is going to bisect this triangle into 2 equal parts, and in that case area opposite to node 1 is going to be half the area, and area opposite to node 2 is going to be half the area of total triangle, total area of the triangle. So, L1 is going to be half, L2 is going to be half, and L3 area opposite to node 3 is going to be 0. So, L3 is going to be 0. So, that is how L1 is going to be half, L2 is going to be half, L3 is going to be 0 for node 4. Similarly, at node 5, node 5 is along side 2 3. So, imagine a line connecting nodes 1 and 5. So, that line is going to bisect again triangle into 2 equal parts, and area opposite to node 1 is going to be 0, area opposite to node 2 is going to be half the area, and area opposite to node 3 is going to be half the area. So, in that case L1 is going to be 0, L2 is going to be half, L3 is going to be half. Similarly, for node 6. I hope this is clear. So, now you can easily verify that L1, L2, L3 for all these written for all these nodes, they are not whole numbers, because we have half for some of the quantities. So, what we need to do is, so that is why if required we need to normalize. So, that is second step. So, now here it is required. So, multiplying all coordinates by 2 gives us whole numbers. So, multiply for node 1 you take multiply L1 with 2, L2 with 2, L3 with 2. So, we get 2, L1 is equal to 2, L2 is equal to 0, L3 is equal to 0. Similarly, if we take node 4, L1 is half. So, multiplying that with 2 we get L1 is equal to 1, L2 is equal to 1, L3 is equal to 0. So, using these new node numbers, we can write 3 subscript numbering scheme like this. So, L1, L2, L3 are normalized with the 2 to convert into whole number, and they are written side by side for each of the nodes L1, L2, L3. That is how we obtain this 3 subscript numbering scheme for 6 node triangle. So, this is how you can obtain this 3 subscript numbering scheme for any triangle, any noded triangle. So, once we have this, next step is, once the nodes are numbered with 3 subscript numbering scheme, shape functions can be written using the following interpolation formula. So, now each of the nodes 1, 2, 3, the numbering is replaced with 3 subscript numbering scheme. So, each node is referred to with respect to 3 subscript numbering scheme. So, the corresponding shape functions can be obtained using this formula. Nijk is equal to Ai L1, Aj L2, Ak L3, and Ai Lj is defined like this. P goes from 1 to I depends on the value of subscript for Ai, and N is the order of trial solution. It depends on what noded element you are looking for. If it is 3 node triangular element, it is linear, it involves linear functions. So, n is equal to 1. If it is 6 node triangular element, it involves quadratic functions, and so n is equal to 2, and if it is 10 node triangular element, it consists of cubic functions. So, n is equal to 3. And here in this formula we have the symbol pi, which indicates product of terms in series. So, first term multiplied by second term multiplied by third term like that. And note, the number of nodes in a triangle is equal to the terms in a complete 2 dimensional polynomial of appropriate order. Suppose one is looking for a triangular element of certain order, that is linear order, in the sense we are referring to whether it is linear element or quadratic element or cubic element. If one is looking at a triangle element of certain order, then one has to include all the terms in a complete 2 dimensional polynomial of that particular order. So, now let us see, and these terms are coming from the table as given here. Table below lists the terms in 2 dimensional in a 2 dimensional polynomial up to 4th order. So, n is equal to 0 corresponds to constant. So, it consists of only 1. A linear element consists of functions. In the trial function of a linear element, we will have 1 x y, and it consists of 3 nodes, and in a quadratic trial function we have terms 1 x y, x square, x y, y square. So, we need to take n is equal to 2, and it corresponds to 6 node triangle. Similarly, if one selects all the terms up to cubic order, so then 10 terms total in total trial solution will have. So, the triangle element is of order 3, it is going to be cubic, n is equal to 3, and it should consist of same number of terms as the number of nodes in a triangle should be equal to number of terms. So, it should consist of 10 nodes. Similarly, a quartic triangle element consists of 15 nodes, and it consists of 15 terms, which are all the terms shown in the table, which can be easily verified, which counts to 15, and the order of element is going to be quartic. There is a print mistake there, it should be quartic, and n is equal to 4. It also gives the required number of nodes for triangular element of different order. So, we can extend this table and we can easily get what are the number of nodes required for triangular element of different order. So, now let us try to understand how we can apply this formula for deriving shape functions for 6 node element, for which we already found what are these L1, L2, L3, and we already looked at 3 subscript numbering scheme. So, we are ready to use this formula because we already have 3 subscript numbering scheme for each of the nodes. Three subscript numbering for nodes was developed in an earlier example and is shown in figure below. So, now we are ready to use the formula. So, n1 shape function corresponding to node 1 is equal to n 200, and before that we are dealing with 6 node element. So, for quadratic it is a quadratic element, n is equal to 2, and so the formula for all a's ai here substituting into substituting the 3 subscript numbering scheme corresponding to node 1, that is 200, into the interpolation formula that we have seen in the earlier slides, we get shape function corresponding to node 1. Before that we require to calculate what are these a naught Lj, a1 Lj, a2 Lj, because these will be required when we are actually using the interpolation formula. So, a naught Lj using the formula for ai Lj can be verified as is equal to 1, a1 Lj again here I takes value 1. So, the counter over this pi goes from p is equal to 1 to 1, which gives us only one term. So, a1 Lj turns out to be 2 Lj, and also it can be verified that a2 Lj I takes values 1 and 2. So, counter goes from 1 to 2. So, 2 terms we need to take product of those. So, finally, it results in Lj times 2 Lj minus 1. So, depending on j value we can use this a naught Lj, a1 Lj, a2 Lj. So, for a particular node with 3 subscript numbering scheme, this is the formula. So, now in the figure on the right hand side, all the 3 subscript numbering scheme for all the nodes are shown. So, shape functions for node 1 is same as in 3 subscript numbering scheme, node 1 corresponds to 200. So, n subscript 200, that gives us I is equal to 2, j is equal to 0, k is equal to 0. So, substituting into the interpolation formula we get this, and now after that we need to substitute what is this value of a2 L1, a naught L2, a naught L3 by substituting all those and simplifying. N1 is equal to L1 times 2 L1 minus 1. Similarly, shape function for node 2, node 3 and node 4, node 5 and node 6. With appropriate change of variables, all integrations and differentiations necessary for developing finite element equations can be carried out in the natural coordinates. If necessary, the shape functions can also be expressed in terms of x, y coordinates, which we will see in an example. So, this is how shape functions can be calculated. So, now let us take an example. For right triangle shown in figure below, develop explicit expressions for shape functions in x, y coordinates. So, all the coordinate information is given in the figure. So, we can easily calculate what are L1, L2, L3, which are required for writing the natural coordinates of all the nodes, and also finally to get 3 subscript numbering scheme. So, L1 is given by this formula, and to find L1 we need to calculate what is AT and A1, they are also shown, and finally we can calculate L1, and also to calculate L2 and L3 we need to know what are A2 and A3. So, those are also shown here, and using that and AT we can calculate L2 and L3. So, L1, L2, L3 for this particular right triangle with the coordinates that are given by this L1, L2, L3, and in the earlier example we have already derived shape function for all the 6 nodes in terms of L1, L2, L3, and for this element, for this right triangle element we got L1, L2, L3. So, now we need to substitute that those values of L1, L2, L3 into this, and then we can get the shape functions for all the 6 nodes. In terms of x, y. So, this is how one can derive shape functions for higher order triangular element, and not necessary in x, y coordinate system, but we can also derive in parent element coordinate system, that is in S and T. So, now let us look at mapping for triangles. Consider mapping of a linear 3 node triangle like this. A right triangle is shown in the figure on the left hand side, and that is used as a parent element for arbitrarily oriented 3 node triangle element, which is shown on the right hand side. So, the left hand side shows the parent element and the right hand side shows the actual element. So, any element we are going to map onto an element which looks like what is shown as parent element, in which the nodal coordinates are 1, 2, 3, and they are located at 0, 0 node 1, and node 2 is located at 1, 0, and node 3 is located at 0, 1. So, to get the isoparametric mapping, if you recall even the way we did for quadrilateral element, we require to find shape functions in the parent element coordinate system and use the actual element xy coordinates to get the relation between x and s and t, y and s and t, from where we can find all the derivatives of x with respect to s and t, y with respect to s and t, and finally we can get Jacobian and determinant of Jacobian. So, using the formulas that we have seen till now in today's class, to get the shape functions for this parent element in S and T coordinate system, what we need to do is we need to find L1, L2, L3 for each of these nodes, and then for 3 node element L1, L2, L3 are same as N1, N2, N3, that can be easily be verified. So, we need to find L1, L2, L3 for the parent element, parent 3 node element. Natural coordinates for triangle, for the triangle below can be written as follows. So, for this triangle one can easily calculate area, which is going to be, total area is going to be half, and therefore 280 is going to be 1, and LT, as I mentioned, replace, when you are trying to find what is LT, replace the first column of the numerator with, instead of x y, since we are dealing with s and t, replace them with s and t, and the second column and third column consists of nodal coordinates of node 2 and 3, and since total area is equal to 1, so denominator is going to be 1. So, L1 is given by this, L2 is given by this, L3 is given by this. So, we got L1, L2, L3 for these nodes. So, using the 3 subscript numbering scheme, the shape functions for this triangle can be readily written, and you can do that as a part of homework, and it can be easily verified that L1 is same as N1, L2 is same as N2, L3 is same as N3. So, we got shape functions N1, N2, N3 of the parent element, and we also know the coordinates of all nodes of the actual element. So, we can easily write the mapping. These shape functions can be used to map an arbitrary triangle into right triangle as follows. This expression looks similar to what we have earlier for quadrilateral element, except that here L1, L2, L3 are used, because L1, L2, L3 are same as N1, N2, N3 for only for 3 node triangle element. Okay. So, x is, and substituting L1 in terms of S and T, L2 in terms of S and T, L3 in terms of S and T, we get relation between x and S and T and y as a function of S and T. And now use we can easily verify from these 2 equations, when S is equal to 0, T is equal to 0, substitute S is equal to 0, T is equal to 0, that corresponds to x is equal to x1 and y is equal to y1. Similarly, S is equal to 1, T is equal to 0 gives us x is equal to x2, y is equal to y2, and S is equal to 0, T is equal to 1 gives us x is equal to x3, y is equal to y3. So, thus an arbitrary triangle in the xy coordinate system is mapped to a right triangle in the S and T coordinate system using this terminology, using the terminology used for isoparametric elements. The right triangle is parent element for arbitrary triangular element. and this mapping concept is as well valid for higher order triangle elements and those with curved boundaries. And let us take quickly as an illustration, consider a 6 node quadrilateral 6 node quadratic triangle element with curved boundaries. So, physical element is shown and also, or the physical element is same as actual element with curved boundaries is shown on the left hand side, and parent element is shown on the right hand side, and all the coordinates are indicated for the parent element. The intermediate nodes are located at the midpoint of each of the sides. So, with the information that is given for parent element coordinates, we can easily derive what are the shape functions by calculating L1, L2, L3 for each of the nodes. And once we get L1, L2, L3 for each of the nodes, we can easily find what is isoparametric mapping for this particular element, which is going to be x is equal to n1 x1 plus n2 x2 plus n3 x3 plus n4 x4 plus n5 xy plus n6 x6. Similarly, y isoparametric mapping for y, but to use these two expressions we require n1 to n6 of parent element. For 6 node element, we already seen earlier in today's class the shape function expressions for n1 to n6 in terms of L1, L2, L3, and also L1, L2, L3 we already have. So, using that information we can write shape functions for all the nodes n1 to n6. So, once we have this shape function expressions, we can write isoparametric mapping, and also we can find derivative of shape functions to finally calculate Jacobian and determinant of Jacobian using these relations. We will see applications of these equations in the next class, again to check the validity of mapping for triangular elements. And similar to quadratic elements, the determinant of matrix J is called Jacobian. Since it appears in the denominator in the above equation, it must not be 0 anywhere over the domain. Mapping is not valid if determinant of J is 0 anywhere over the element. So, these are all these points are similar to that for quadrilateral element that we already looked at. For 4 node and 8 node quadrilateral elements, validity check we already performed. So, similar points we already took care for those elements. So, same points are valid here. So, with this we will continue in the next class.